How are you, everybody, or digital electronics engineering students? I would like to take this opportunity to welcome you into these very interesting moments of learning about digital electronics. If this is the first workshop for you or lecture for you, my name is Olenjolai. I'm very happy to have you. And I would like to welcome you into these very interesting moments of learning about the new topic that's called universal logic gates. I have some physical students who have joined in this class from different fields of engineering because these contents are very important for electronics engineering students, are very important for telecommunication engineering students, are very important for mechanical engineering students, are very important for mechatronics engineering students, are very important for biomedical engineering students, and these contents are very important for electrical engineering students and are very important for computer engineering students. So I think that I've prepared very important information that can help you or can take you from one point of understanding to the next point. So I don't want to waste much of your time. I think that you are well prepared. Have a fresh mindset. Have a pen, a pencil for drawing because we are going to have very interesting drawing. But one thing which I want to tell you that the name of the lecture workshop is the workshop 5. It's actually named Nandi and the NOR gate. These are not actual new gates or new phenomena in the mind of engineering students, but I want to tell you that we are going to learn them practically. We have been learning them theoretically and especially by using different schematic symbols. But when we are going to learn in this class, we are going to learn and think them, how we can use them or how we can interconnect them together in order to perform a particular functions in electrical, electronics, or mechatronics. So I think that that introduction is enough. Let us go to the business, but let me appreciate some engineering students who are in this class. How are you, students? Yes. Okay, are you ready for today's workshop? Yes. Are you ready? Yes, sir. Well, thank you very much. So we don't have a quick review of what we've covered because this is the new topic. We have to go straight forward and just understand the concept. And the first terminology that you want to understand is the meaning of this word universal logic gates. Class A, universal logic gates. Universal logic gates. Say universal logic gates. Universal logic gates. So ask your neighbor, what do you understand? What do you understand about the word called universal? So ask your neighbor, universal. Something called, this is universal. I know that you know universal modem, universal something. So what the means of universal? So what is, so you have to think the meaning of the word universal. Once you understand its meaning, then you can predict what are we going to learn. So universal logic gates. What is universal logic gates? There's a different way that you can define this terminology, but this is the one of the way that you can define. A universal logic gate A universal logic gate, we say that is the type of logic gates that can implement this is the type of logic gates that can implement any Boolean function, without the usage of any additional logic gates. So this is the one way that you can define the word universal logic gates. So universal logic gates, this is the type of the logic gates. It's just like a fundamental or basic logic gates. That's the one of the types of the logic gates. But the goodness of these universal gates, we can implement what? A Boolean function without the usage of any additional logic gates. So universal logic gates, once you have it, you can implement any Boolean function that you want without using any other logic gates. That's the meaning. So the meanings of this word that universal, it means it have multiple usage. You can use it in designing different digital circuits which actually perform an operations about a particular Boolean functions. So once you have one universal logic gates, you don't need some other gates. Why? Because you can find other gates within these universal gates. Are we together? Yes. Class, are we together? Yes. Okay. Then the universal gates, what are the universal gates? There are only two, but they have changed the word. The universal logic gates. The universal logic gates are there, or are Nand and the NOR gate. So are the Nand and the NOR gate. There are only two gates that we call them universal. Say Nand gate. Class, say Nand gate. Say NOR gate. So these gates are called the universal logic gates because you can use them to implement a combinational digital circuit that perform any Boolean, any logical Boolean expression, any logical Boolean expression. So that's why we call them universal gates. So the following are some of the logic gates that can be implemented by using NAND gate. So you can use NAND gates to implement the following logic gates. You can use the NAND gate to implement NOT gate. You can use a NAND gate to implement AND gate. You can use the NAND gate to implement the OR gate. You can use the NAND gate to implement the NOR gate, etc., etc., etc. You can use the NAND gate to implement exclusive OR gate. You can use the NAND gate to implement exclusive NOR gate. That's why we call them universal. Also, the following are some of the examples of logic gates that can be implemented by using the NOR gate. So the first one is we can use the NOR gate to implement NOT gate. You can use the NOR gate to implement AND gate. You can use the NOR gate to implement OR gate. You can use the NAND gate or the NOR gate to implement NAND gate. Also, you can use the OR gate to implement XOR gate. You can use the NOR gate to implement exclusive NOR gate. So remember that those some examples of logic gates. They perform differently logical Boolean operation. Is it clear, students? Eh? So from this description, once you have an AND gate, you can implement the 3 basic logic gates. Stop writing. Once you have NAND gate, either 1 or 2 or 3, depends, or 4 or 5, you can implement the 3 basic logic gates. Right? Once you have a single or multiple NOR gate, you can implement the first 3 basic logic gates. But also you can use the NAND gate to implement the NOR gate. Hello? You can use the NOR gate to implement the NAND gate. That's why in the definition we say that you just need NAND gate to implement all or any Boolean expression that you want to implement by using them. Okay, so when we've been discussing about let me touch something about when we've been discussing in chapter 2 about basic logic gates of fundamental logic gates, I forgot to discuss with you about Boolean expression. We just discussed Boolean expression of NOT gate. We didn't discuss Boolean expression of other logic gates. So Boolean expression of AND gate. Boolean expressions of 40 of AND gate. Stop writing. These are the simple concepts, especially for concept about Boolean expression. With regard of logic, as the third topic of advanced physics from 5, we used to present these multiplication operations of NAND gate by using these symbols. Do you remember that? So by that time we say that A, we call it what? Conjunctions or disjunction. Conjunction what? B. Right? But in logics we don't use that symbol to show that. So the symbol for the AND gate is just a dot. So for instance, if you say input A and the input B, this in Boolean expression, we just write A dot B, which you call it what is equal to Y. So simply the Boolean expression is Y is equal to A and B. Or we don't write the dot, we just write AB. So whenever you see the Boolean, hello, friend there, you are writing very good. Whenever you see a Boolean expression like this one, whether for the 2 inputs, or for the 3 inputs, or for the 4 inputs, you have to know that in between A and B we have AND gate. Okay? Should I repeat? Yeah, so one of my friends has said yes. Remember that we design digital circuits or digital or combinational logic circuits sometimes by using the truth table, sometimes, and also we have to use the Boolean expression. So as the serious students in digital electronics, you have to know the truth table of the particular system, and also you have to know how you can reduce the Boolean expressions from the truth table, and how also you can draw the logical schematic circuit diagram from the truth table. So that's what I told you, that whenever you find in Boolean expression with 2 input or 3 input or 4 input, mainly it means that with, yes, we can have 4 inputs, but we have to use more than one AND gate, right? So whenever you find it and you see A dot B, this means A and B. So these are the 2 inputs, but these 2 inputs are fed into the AND gate. Or when you see as AB, then this means A and B. Are we together? Sometimes you may have the Boolean expressions of AND gate, which is A dot B, let's say, dot C. Or sometimes this one we write A, B, complement, so just because not B and C. Okay? So for this case, we have 2 gates. Hello? The first gate is what? AND gate. But also you have NOT gate in one of the input. You see how you define them? C, we can have 4 inputs. A, B, dot C, dot D. For this case, in terms of number of logic gates, are 3. But in terms of the types of the gates, are only 2. And a NOT gate. But you have two NOT gate and 1 AND gate. But it depends. If you are using the AND gates with 2 inputs, then we are going to have a number of them. So this one we can also write in this form. A, B bar, C, D. So it depends. For instance, if we draw the schematic circuit diagrams of this, then we can say that, okay, fine. We can have, for the 2 inputs, this is the AND gate. And then, so this is input A, input B. Then you have also the other ones, the other AND gate. Well, so you have 2 inputs. No, sorry. So we are going to have another AND gate, but here we have NOT gate. So this is C. Huh? No. Why no? B. Okay. Just the labeling. C, this is B. That is correct? So if you have used the two input AND gate. If you have used the same schematic circuit diagram can be present. So remember that we have to use the inputs, the real inputs, the actual inputs. So if you are using the AND gate of 3 inputs, then our schematic circuit diagram for this Boolean expression will be this one. So this is Y. This is A. This is B. This is C. This is Y. Are we together? So that is how you can relate the Boolean expression with what? With the schematic, logical, circuit diagram. So just remember that whenever you see either dot or you don't see the dot, but you see 2 letters, then you have to know that that is all about what? And the NAND and what? AND gate. I'm talking about AND gate. I just went back. This is the concept that we forgot to cover it in previous workshop or lectures. That's why that I went back. I'll come back to the NAND and the NOR gate. Okay? Yes, because some students say, sir, you are teaching NAND and then they are AND. Oh, you forgot N. No. Because some students say, sir, I think you forgot N there. Okay. So then, the Boolean expression of NOR gate. The Boolean expression of NOR gate. Class A NOR gate. OR gate. We are not yet in OR gate. NOR gate. So the Boolean expression, we say that we just write A or B. This we may call it Y. And then this one, we just write it A plus B. So whenever you see plus in Boolean expression, means OR gate. Okay? For that case, we should not leave. For the dot, we can leave it. We may write the dot or we may not write. But for the OR, we have to write. Okay? So this is for the 2 inputs. If you have 3 inputs, then A plus B plus C not gate, or plus not gate C. So how many gates do you have here? 2. The first one is OR gate. The second one is NOT gate. Very good. Then we have another Boolean expression, which you say A plus B plus C plus D. How many NOT gates do you have? How many OR gates do you have? 4 OR gates. First of all, if you want to know the number of OR gates, you have first to define you are going to use OR gate of 2 inputs or 3 inputs. Right? For the 2 inputs, how many OR gates are we going to have? Assistant Sierra is busy writing. If you're using 2 or 2 input OR gate, how many OR gates are we going to have? A? 3. Others, no idea. If you're using the OR gate of 3 inputs, how many OR gates are we going to have? 2. Are you sure that's 2? So if you're using 3 input OR gate, then you are going to have 6 inputs, while there you have only 4. So it means that you don't have an option to use what? 3 input OR gate. You may use a 1, 3 input OR gate and 1, 2 input OR gate. Okay, those are the simple questions. Once you do practice, then whenever you see Boolean expressions, you can predict that the number 40 of gates. So for instance, this one, let us try to draw. It's like, let us just use the 2 input OR gate. Just let us translate the Boolean expression. So this is input A, input B. Then again, we need to OR. So this is A or B or not C. So then we have our OR gate. And this is Y. No, not yet. Then you have D, not of B. So this is D. So D, this is Y. Okay? Okay? Somebody may be given a Boolean expressions, draw the schematic logical circuit diagram. Or you may be given a schematic logical circuit diagrams, draw the Boolean or write the Boolean expression. So you have to learn how to translate from this form to this form or this form to this form. Are we together? A. If you are using 3 input OR gate, then this is the deal. What is going on to that mobile phone? So this is input A, input B, input C. Then so for this case, we have used the 5 logic gates. We have used the how many logic gates? Oh, this is the mistake. We have used the 5 logic gates, right? With this is schematic. Oh, so why are you busy writing? What are you writing? Listen. With this is schematic, we have how many gates? How many gates? 4. For this case, how many? 5. So each design has its advantage. But always, we say the best design is the one that uses the minimum number of 40 logic gates. Okay? Class, are we together? So these are the same schematic or logical schematic circuit diagram. But just the difference is the number 40 of gates. They share the same Boolean expression. So remember that for this case, we have learned the Boolean expression for the AND gate and NOT gate. And for this case, just in OR gate and NOT gate. Later on, you can actually learn or find the Boolean expression which consists of all the types of the logic gates. All the 7 types of the logic gates. So you have to do practice and you have to think. Are we together? Remember that all of these Boolean expressions and the schematic circuit diagram is for the learning purpose. Practically, we don't have any AND gate or NOT gate with 2 pins or 3 pins. So if that concept is clear right now, let us move on. Then, ladies and gentlemen, now let us learn about NAND gate. Say NAND gate. NAND gate. Again? NAND. A? NAND gate. Are you sure? Ask your neighbor, are you sure really you are pronouncing Nandigate? Pronounce it Nandigate. Say Nandigate. Nandigate. Hey, tell your neighbor you are welcome to class. Thank you very much. What is Nandi Gate? So you say that in Nandi Gate is the type of universal logic gate. So let us talk now practically. Logic gates that that performs the logical inverse. The logical inverse of an AND gate. So NAND gate is the types of universal logic gates that perform the logical inverse of an what? AND gate. Okay, so before you learn about NAND gate, you have to learn about the inverse of the gate, and also you have to learn about the AND gate. Because NAND gate is just a combination of 40 inverse or hex, just to call it NOT gate and what? AND gate. So in a simple language, we may say that because we are engineers, NAND gate is equal to AND gate plus NOT gate. NAND gate is equal to what? A. This is not the end now. This is plus. Because for you, you have claimed plus is E. Is OR gate. So you can say that NAND gate is the AND gate or OR gate, NOT gate. So NAND gate, simply say that we do inversion of the AND gate. What is the AND gate? Ask your neighbor. What is the AND gate?
What is AND gate?
Ask your neighbor. Ask your neighbor and wait the response. AND gate is AND gate. What did she say? She's busy right now. She's busy writing and drawing. What did she say? She said nothing. What did you tell her? You are thinking. What did you tell her about AND gate? Tell her AND gate is. So tell her. Yes. Tell your neighbor. AND gate. What is AND gate, Pili? Komba, thank you for trying, Pili. Komba, hey, you're asking your neighbor. It's not the time for asking your neighbor. Yes, it's time for Komba.
With an expression which gives the output of high when it satisfies high and high rise from.
Thank you very much for trying. Komba. So the question is still there at Komba. What's your name? Sophie. So Sophie has tried. Komba, tell us. We learned in previous lecture. So now Pili is going through the previous lecture. Mohammed? What is AND gate?
AND gate, the type of gate that perform multiplication.
Very good. So AND gate, this is the type of the basic or fundamental logic gates that perform multiplication of input binary or binary inputs. So you just define that you provide high when high. So what is that high? 1, 1, eh? Aha. Okay. So the AND gate multiply the what? The binary input. Then now the NAND gate invades what has been multiplied by the AND gate. So invades in what? If the product of the 2 bits is high in AND gate, then in NAND gate will be low. Okay? So NAND gates, that's why you say that it is the providing or perform the logical inverse of what? AND gate. So that's why you say that NAND gate is simply AND gate plus what? NOT gate. Then let us summarize the information for the practical purpose. Schematic symbol. The schematic symbol of NAND gate. Schematic symbol of NAND gate. So this is the schematic symbol of the NAND gate, but especially that let us say that to input NAND gate. So we have the AND gate first, and also we have the NOT gate. So this is inputs, and this is the output. So input, this is input A, let's say, input B, and then this one we can call it intermediate bits, and this the output. So this is for the 2 inputs AND gate. For the 3, so all the same schematic symbol can be drawn in this style. So this is why. So we have inputs, we have output. For the 3 input, is actual, you'll find it's in this style. A, B, C, Y. So these are the simple schematic symbols of 40 of NAND gate. So NAND gates mean that the inputs is firstly fed into the AND gate, and then the output of AND gate, it's the input of 40 NOT gate. That's all. Then the next important information is, before we go for the timing diagram, Boolean expression. Boolean expression. Boolean expression of NAND gate. Say Boolean expression. So the Boolean expression of the NAND gate is this one. Output, then we say what? So outputs of the NAND gate It will be actual. For instance, we have two inputs, A and B. Then the outputs of A and B has to be fed to the input of NOT gate. Or sometimes you can find that this one is written AB, then bar. So that is NAND gate. Remember that. The NAND gate cannot be this one, A bar and B bar. This is not NAND gate. Remember that. A, what do you mean? A and B, NOT gate. This is not equal to A and B bar. A bar, B bar. And also remember that, as the serious students, AB, this is not equal to A bar, B bar. Those are the different Boolean logical expression. Is it clear? Huh? Class, is it clear? Yeah, so you have to be careful. Should not cram, just understand and have the concept. For the three input, then we say that the Boolean expressions of the AND gate, we expect it to have A dot B dot C bar, or we call it A, B, C bar. For the four inputs, we may have A, dot B, dot C, dot D. This one also is A, B, C, D bar. So I think that now digital is becoming digital, right? Because what you are writing on the blackboard is just the symbols and equations, diagrams, equation. So it becomes very interesting. So remember that this is one AND gate, two NOT gate, right? While this one is one AND gate, one NOT gate. That's the difference. Okay, so once we have covered, or is the concepts of Boolean expressions of NAND gate, is it clear? Eh? Okay. So now let us discuss about timing diagram. Before timing diagram, because I know my students will not understand the concept of timing diagram before we cover the concept of the truth table. Truth table of NAND gate. So once we draw the truth table of NAND gate, then you can understand the timing diagram. So let us start for the two inputs. The simplest way of drawing the table or the truth table is this. We have inputs, we have output. For instance, for that point, one input is called E, the other one's A, it is B, then the other one is called what? It's called D, we call it P. Then the output is Y. Stop writing, please. Look on the blackboard and listen. This is our truth table. Okay? A. So in previous workshop, we said that fundamentally, we may use just the say that letters called 00011. So for this one, we may call it 1010. Because this is the possible combinations. Stop writing, stop drawing. Then for this one, we may also say 1, 1, 0, 0. It's fine. We reversed what you have been known. We discussed it in previous workshop. Should not claim the truth table and the arrangements of the bits in inputs. Okay? You have to be flexible, but the truth should remain the same. Okay? I know for you what you have been claiming. This, first of all these bits should be here, and it should start 0, 0, 1, 1. Then this bit should be at the input TB, and it should start 1, 0, 1, 0. Otherwise, further information should be provided. Danny, where is the Simon? Yuda? Look for him, please. He has been lost in the class. Okay, so then where is the point we call TP? This one. Right? Stop writing. So this is the point TP. So 1 and 1. Good luck. Go and wash your face there outside. Hurry up. 1 and 1. Yeah? 1 times 1. Yeah? Are you sure? Can you prove? 1 times 1, it's a 1. Then not inverse of 1. Yeah? 0. Very good. Then 0 times 1. Huh? 0 in binary number or in decimal number? Eh? Eh? In binary. In decimal number? Both. So my friend has said both. However, that he was not present, but he understood. What is decimal number? That's none of your business. Okay. So 0 times 1, whether in binary or decimal number, the answer is 0. Right? Then inverse of 0. 1. 1 times 0. 0. Inverse of 0. Then 0 times 0. Agape, 0 times 1. 0 times 1 times 1 times 1. 1 times 1 times 1 times 1 times 0. Very good. Agape is in the class. 0 times 0 it is what? 0. Inverse of 0 it is what? 1. Remember that drawing these two tables and whatever, it's not a great deal. It's not a tough job. The issue is to translate them practically. That's another story. Okay? So this is just a review of what you've covered in advanced electronics science. But we are heading to the point where we add the value in engineering. Okay? So this is what Sophia wanted to present, and Mr. Who and Pete. So then now 3 input NAND gate. And the great deal actual is not even to draw. It is to relate these concepts or to draw these concepts into real life application. How can you use these logic gates to solve a real life problem? So here we have inputs, here you have outputs. So input A, input B, input C, output Y. One, two, three, 4, 5, 6, 7, 8. Then arrangements of the bits, you should not claim. 0, 1, 0, 1, 0, 1, 0, 1. Hello? Hello there? Then you can say 1, 1, 1, 1, 0, 0, 0, 0. Right? You should not worry. You have to reverse them the way that you can. Then we can say that 0, 0, 1, 1, 0, 0, 1, 1. I know that you are expert on starting with what? 0, 0, 0, 0, 1, 1, 1, 1. Do you know that you're expert? And you're expert to say that 0, 0, 1, 1, 0, 0, 1, 1. And then say, okay, we finish with 0, 1, 0, 1, 0, 1, 0, 1. So that is reclaiming. That's why that when we ask you, okay, you have understood the two-step way, where can we apply in mechanical system? That's none. That's out of the syllabus. Maybe that's the master's program. Are we together? So I told you that you should not claim about the remains of these bits. These are the possible combination, actual that they can take them or they can take in different directions. So some of the students, they can say, sir, it's not true. It's not like the previous one. No, it's true. Okay? Yeah, but for you, I know it's a new business, so you have to take some time. 0 times 1 times 0. Yeah? Inverse of 0. 1. So the output bits for this case, for this possible combination is what? 1. 1 times 1 plus 0. Eh? 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 1. Very good. Those are the one who had. I said 1 times 1 plus 0. I know you prepared the 0. Because you expected me to ask you 1 times 0. So I deviated it there. I shifted the venue. The IT used to call that Mwalimu amehama venue. From B12 to W. Okay, so 1 times 1 times 0, it is 0. Inverse of 0, 1. 0 times 1 times 1 times 1 times 1 times 1. 0. Inverse of 0, 1. 1 times 1 times 1 plus 0. You have to take some time to think about that. But 1 times 1 times 1, no, you have the response already. So 1 times 1 times 1 times 1? 1, right? Inverse of 1? 0. 0 times 0 times 0 times 0 plus 1? 0 times 0 times 0? Plus 1, is equal to 1. So 0 times 0 times 0, 0, right? Inverse of 0? 1. Then 1 times 0 times 0? Inverse of 0? 1. Then 0 times 0 times 1? Inverse of 0? 1. 1 times 0 times 1? 0. Inverse of 0? 1. So the output of NAND gate is 0 when all of its inputs are 1. So remember that the issue is not to draw this truth table. The issue is just to combine these bits. No, the issue is how you can use this knowledge on solving real life. That's the challenge. So from this truth table, we say that, not before. So that's what Sophia and Pili was stating. The output of the NAND gate is 0 or low when all the inputs are high or 1. That's very important. So whenever you're thinking about digital circuits or digital system, where that the output will be 0. When all the inputs are high, then NAND gate will be a good choice. Okay? Yeah. So remember, when you say high, we don't mean 5 volt. We may mean 5 volt or 0 volt. When you say low, we mean 0 volt or 5 volt. Should not claim. So then the next part is what? Timing diagram. Tell your neighbor it's a time for timing diagram. Timing diagrams of NAND gate. Tell your neighbor, however that your neighbor is tired, Tell him or her, it's time for timing diagram of NAND gate. Tell your neighbor, please. Hello, where are you going? Hello, hello, hello. It's a time for what? Timing diagram. Gaudens, where is Edison? I told you that you have to protect him. You have to be with him. Hand to hand. Because that guy is dodging a lot of session. Okay? So you failed the responsibility that I gave you. So now you are going to draw what? Timing what? Diagrams. Timing diagrams means what? Representations of what? Falling time and raising time of the digital signal in the NAND gate. Are we together? Okay, so stop drawing and stop writing. So let us draw the timing. So I don't have enough space. We can draw the timing diagrams for 3 inputs. We have been drawing for the 2 inputs, but I think that the space might not be enough. Should we draw for this or for this one? 3 inputs, yeah? Yes, because you like to simplify life, eh? And you draw for the 2 inputs, is it? Yes, you are Tanzanian students. So, as Tanzanian students, we like simplicity. We like bargaining and we like simplicity. If you have gone to Kariako, you know the meanings of bargaining. The price might start with 30,000 and the final price might be 2,000. That is Bongoland. So if you accept 30,000, it means you have actual support the business with the profit of 30 times. Because the items might be, maybe the buying price for the items is 1,000 or 500. So you say, okay, 30,000, then you provide. Okay. So then let us draw for the timing diagrams of these 3 inputs NAND gate. So let us start with input A. Stop writing, stop drawing, please. Stop writing, stop drawing. Let us draw together. I want you to be competent in drawing timing diagram. So first of all, we need what? We need the dotted lines, isn't it? How many? A? You don't understand. 8, yeah? Are you sure? Ask your neighbor, did you understand why are we saying 8? Ask your neighbor, did you understand why are those guys mentioning 8? 1, 2, 3, 4, 5, 6, 7. So let us start with input A. I said, stop drawing, listen, and watch. So the input A, the first bit is 0. Right? A. The second bit, high. Are you sure? It's 1. The next bit, 0. Dala. The next bit, the next bit, here we have 0. The next bit, A. Are you sure? This is input what? A. Then input B. The first bit for input B is what? So 1. The next bit for input A, 1. The next bit for input A, B, 1. The next bit for input C, 0. Who told you 0? 1. The next bit for input B, 0. The next bit for input B, then the next one, are you sure? Ask your neighbor, do you like zeros nowadays? In terms of marks of the test assignment? No, you don't like. But in digital, you like zeros. Then C. You've been waiting for C, eh? Tell me for C. The first bit for C? 0. The next one? Next C? 1. And next C? 1. And next C? Next C? And next C? 1, 1. Then we have the output graph. So in the output graph, what do we have? The first bit is what? A? 1. The second bit is what? A? 1. The fourth bit is what? A? 0. The next bit is what? 1. The next bit is what? 1. The next bit is what? 1. So this is our timing diagram. Is it interesting? So that the timing diagrams of 40, Nandi, or 3 input 30, 3 input Nandi, gate. So then the next concept that we have discussed, it is physical appearance. Physical appearance, or we call it internal structure of Nandi gate. So example of Nandi gate is SN74HC00N. Okay, so my dear students, let us continue with our lecture 4 of Nandi gate, and let us focus on the physical appearance of the Nandi gate. And our Nandi gate that we are going to focus is SN74HC00. So this is a quadrature, or just it means that this integrated circuit, it consists for Nandi gates. So it consists for Nandi gates. So let me just draw the large integrated circuit. So let us start with the physical appearance of the Nandi gate, and then we'll finish up, or we'll end with the schematic circuit diagrams of Nandi gate. So the SN74HC0, this is transistor logic. So we have some pins here. We have 14 pins. The third pin, first pin, one, two, three, four, five, six. This is pin number 7. So this one, we call it TOT class notch. Say notch. So notch is actually help us to know about the numbering, the universal numberings of the integrated circuit. So how do we number? So this is pin number 1, pin number 2, pin number 3, pin number 4, pin number 5, pin number 6, pin number 7. This is pin number 8. This is pin number 9, pin number 10, pin number 11, pin number 12, pin number 13, pin number 14. So pin number 7, this one we call it ground. So common ground dot pin. And then pin number 14, this one we call it VCC for power. Then we have 14 pins remain. 1, 2, 3, 12 pins. 1, 2, 3, 4, 5, 6. No, it means we have 6. And then 7, 8, 9, 10, 11, 12. So all of these 12 pins, some of them will be used as the input pins, and some of them will be used as output pins. So pin number 1, according to the data sheets of SN74HC, pin number 1 and pin number 2, these are the input of Nandi gate. And pin number 3, this is output of Nandi gate. Again, we have pin number 4, and pin number 5. These are the input of the Nandi gate. Then pin number 6 is an output. Again, pin number 10 and pin number 9, these are the inputs of the SEDI Nandi gate. While pin number 8 is the output of the SEDI Nandi gate. Pin number 13 and pin number 12, these are the inputs of the fourth Nandi gate. And pin number 11, it's an output pin of 40 of the fourth Nandi gate. So ladies and gentlemen, this is figure 3, the physical appearance of what? Of SN74HC00 Nandi gate. Then the last concept that we have to discuss, I have talked about the pull-up resistor, so that we have to use that the input. Now let us focus the schematic logical circuit diagram. Circuit diagram of Nandi gate. What the schematic circuit diagram of Nandi gate. So remember that the general block diagrams that will have the C power supply, and also after having the C power supply, we'll have also the inputs to the NAND gate, and we'll have the NAND gate itself as a control unit, and we'll have the output units where we'll be using just the indicator, the light indicator. It means that the status indicator, which are going to use light emitting diodes. So then now, let us draw our overall schematic circuit diagram. So this is the notch. This is pin number 1, pin number 2, pin number 2, pin number 3, pin number 4, pin number 5, pin number 6. 1, 2, 3, 4, 5, 6. Pin number 7. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Pin number 1, pin number 2, pin number 3, pin number 4, pin number 5, pin number 6, number 7, 8, 9, 10, 11, 12, 13, 14. Okay? So, first of all, we have to supply power. So, we have to connect pin number 7 with common ground. But also, you have to supply power. So, you have to supply VCC, which is 5 volts, to this pin. Okay? Then again, we may use any of the AND gate. Okay? We may use either this AND gate or we may use the other one. So let us use the first AND gate. So in the first AND gate, NAND gate, sorry, the first NAND gate, so pin number 13 and 12 will be input. So then what do we need? So we need to have a pull-up resistor network. So you are going to have resistor. And you're going to have push button and connect to the ground. This is push button number 1. So this is push button number 1. This is resistor, pull-up resistor, 10 kilo ohm. So we draw the input, supply the input from here. Again, we have the other one. We have another push button. So this is push button, so this is resistor, 10 kilo ohm. This is push button number 2. For this case, we're going to have our input. Okay? Then next, this is output. So for the output, we expect to have a current limiting resistor. And then so you're going to have a light emitting diode to indicate the status of the digital output. So this can be ready LED. And here we have a resistance or resistor with resistance of 220. So now this is the schematic circuit diagram. Let us label it first and then explain how does it work. Figure 3, the schematic circuit diagram. You have to write the word schematic logic circuit diagram. Logic circuit diagram of 40 of NAND gate. How does this circuit work? Wonderful. It just have 4 principles. Just have 2 principles, but just you can clarify them in 4 principles. The first state, we say that, remember that if the push button is not pressed, the voltage across push button is 5 volts for this case. That's very important. So the first state, we say that if both push button number 1 and push button number 2 are not pressed, means this is high state, high state. So we have BT1, BT1. 1 and the 1, we get 1. Not of 1, we get 0. So we have 0. So the LED will be off for that state. The second principle. If push button 1 is pressed and push button 2 is not pressed. So for this one, we have 0 volt, and for this one, we have 5 volt. So the 5 volt is supplied to this pin number 12, while 0 volt is supplied to pin number 13. It means that 5 volt and the 0 volt, or 1 and the 0, it is 0. Not of 0, it is 1. So 1, then the LED will turn on for that state. The steady principle of operation is when push button 1 is not pressed, but push button 2 is pressed. So for that case, when it's pressed, So we have 0 volt in pin 12. We have 5 volt in pin 13. So 0 and 1, or 0 volt and 5 volt makes 0. Not of 0 give 1. So the LED will turn on. The last principle of operation, we say that if push button 1 is pressed and push button 2 is pressed. For that case, we have bit 0 in pin 12 and pin 13. And then for that case, 0 and 0, or 0 volt and 0 volt is 0 volt. Not of 0, it's 1. The LED will turn on. So the LED will turn on for the 3 situation, while turn on for the 1 situation, whereby both inputs are high. And that's the principle of operations of Nand gate according to its truth table. Because according to its truth table, we say that when the output is high, when the inputs, both inputs are high, the output is 0. When either input is 0, then the output is 1. So my dear students, that's the end of lecture 4. I thank you very much, and I would like to take this opportunity firstly to thank God who have been with me. And I would like to welcome in the next lecture, that will be lecture 5. And the assignment or the homework I would like to leave to all the students, I explained briefly and with aid of diagrams that we've discussed, it means simply discuss about NOR gate. So that's what you have to discuss and do the further study. So thank you very much. May God bless you. I love you so much. Keep enjoying the beauty of digital electronics. I just want to tell you that stay tuned and stay connected to our official YouTube channel for the more information. Thank you. Bye-bye. Be blessed.
Mungu ibariki Afrika, wabariki viongozi wake, hekima, umoja